And maybe Duncan, do you want to share share your screen now?
Sorry, I missed the first part. My audio wasn't working, or my speakers weren't working.
Oh, I guess we're starting in a minute, so maybe it's a good time to share your screen.
I was thinking the same thing.
Okay.
So
go ahead.
I'll go ahead and do that.
We'll just wait till 1 past for anyone who's still, I think there's a few people still coming back from lunch. Okay, maybe let's get started. So to kick off the afternoon session, we have Duncan Dauvergne from Princeton, and he'll be talking about infection spread in a sea of random walks.
Great. Thanks, Alan, and thanks for the invitation. So this is based on joint work with Alan Sly, who you may know from his introduction of me. So I'm going to be talking about a bunch of different models of infection spread, which is a project we started working on right around the time COVID hit, entirely coincidentally. So the basic setup is the following. So you have a Poisson process. On ZD. So, homogeneous Poisson process, say intensity 1. And all my pictures are going to be for Z2. And think of each point in this Poisson process as a particle, and each of these particles will perform an independent random walk. So these are particles performing independent, continuous time random walks. So these are my little X's, and they'll kind of move around doing their thing on the lattice. And when I start this process, I'm going to add an extra particle, which is this red one here at the origin, and this particle will start out as infected. So this is the rule, is you have one infected particle at the origin, which starts at 0. And okay, it's an infection spread model. So what's going to happen is when an infected particle meets with another particle, so these are going to be susceptible particles, then the susceptible particle will become infected. So at the start, the infected particle will move around for a while till it hits one particle, it'll infect that one, then you'll have 2 infected particles moving around, and they'll maybe spread it to a couple more, and the infection will keep spreading in this way. So when infected meets with a susceptible particle, you get this transition from susceptible to infected. And so sometimes called an SI model, a susceptible infected model. Okay, so this is one really, really basic thing. You can either think of it as a model for the spread of an infection. You could also, in some sense, imagine it as a model for a chemical reaction. You sort of have 2 types of molecules, and when they meet, you sort of have an A molecule and a B molecule, and you meet, and then you create 2 B molecules or something like that. And of course, with infections, we know with certain infections, people can recover and maybe become immune, or maybe they can get reinfected. So you can introduce a few variants of this model, which are interesting, which is just you allow your infected particles to recover. So they'll recover with some rate lambda bigger than 0. So If lambda is large, then they're recovering very quickly. If lambda is small, then they're sort of recovering slowly. And there are two variants you can consider. You can consider the variant where they recover and they're susceptible again. So this is sometimes called an SIS model. So they can sort of keep getting reinfected. Or you can consider a variant where they recover and then are either removed. So that's what the R stands for, removed, or fully recovered, in which case they're immune from the infection. So you can kind of just forget about them and remove them from the whole process. This we'll call an SIR model. Okay. So, you know, these SI, SIS, SIR models, you can set them up in totally different frameworks. This idea of having a sea of random walks and spreading the infection that way is just one model. And it's in some sense, you know, if you tried to do this in a simpler framework, you could say different types of things. You know, this we'll see that this has some interesting features. So these models were kind of first studied by Keston and Siderovicius in the early 2000s, and they proved some really remarkable things. So let me just start with saying what they showed about the SI model. So I'm going to let CT be the set of sites in ZD that have seen an infected particle by time t. Okay, and the first thing they showed is that this set of sites, it kind of grows linearly out from the origin. And they showed something much stronger, which is that CT over T. So if you take this CT and you renormalize it by time, then actually almost surely this converges to a deterministic set K. So K is some compact, non-empty deterministic set. And so this is a shape theorem for the SI model. And I'll emphasize, this is really a highly non-trivial thing, this shape theorem. So when I often think of shape theorems, I think first passage percolation. And in first passage percolation, you have subadditivity, where you kind of get the shape theorem without too much work from the subadditive ergodic theorem. Here, it's a lot of work to get the shape theorem. It's kind of 100+ pages. You know, the culmination of this was the only instance I know of a shape theorem getting published in the Annals of Math. So it really is quite an impressive result. So then you can ask about these other types of models, and SI is the simplest. And the way I think about it is SI is the simplest model. You can prove the most things about it, but when you start to add in, you know, this ability for particles to recover, either and become susceptible or fully immune, you start to see some more interesting phenomena. So what you can see with SIS is you'll have different recovery rates. And what you expect is that if the recovery rate is fast, then maybe the infection should just die out. And if the recovery rate is slow, then the infection should, you know, possibly survive forever. And so you see a phase transition. So this is something novel. And so what they established was a phase transition. Okay, and I'll state this. I'm going to state this, you know, phase transition theorem in two parts. And the first one's kind of trivial, but the first part is that there exists a critical recovery rate between 0 and infinity inclusive. So of course, it's going to depend on the dimension, such that if lambda is less than the critical recovery rate, then the process survives with probability greater than 0. So it's never going to survive with probability 1, because there's always a chance that, you know, this particle that you've planted, which is infected, just recovers immediately and nothing else happens. So, but you can say that it survives forever with positive probability if the recovery rate is small. And if the recovery rate is bigger than this critical guy, then the process dies almost surely. Okay. And in some sense, this point 1 is not very, it's not very, you know, it's not a very difficult theorem. What you have here is monophonicity. So if you try and couple it, I think it's really the most natural coupling of processes with different recovery rates. When you do this with the SIS model, you'll see that in the process with the higher recovery rate, you'll always have fewer infected particles. So you have this natural monophonicity which leads to a monotonicity in this survival probability, which gives you a critical probability. Okay. Okay, and then the second part of this theorem, which is kind of a lot, which is more work, is that this critical probability is non-trivial. So it's not equal to 0 and it's not equal to infinity. Okay. So then maybe, so then you can ask about the SIR model. And there are, so based on, the study of the SI model and the SIS model, there are really two goals you can think about. You can think about, okay, can we establish a phase transition for the SIR model where particles are going to recover and become immune? And even beyond that, is there going to be a way to actually prove a shape theorem? So I can say in this SIS case, you might expect that if the particle, if you know the particle survives and if you know the particle survives forever, what should be happening is that you also see a shape theorem in this setting. Now, Keston and Sidorvicius didn't prove this, and one of the reasons is because there's many more complications in the SIS case. So the dreams would be establishing sort of a phase transition and maybe a shape theorem. And actually, both of these are open questions. The difficulty with the phase transition is this first point, that this process doesn't have any obvious monotonicity. So the natural coupling, or any kind of natural coupling that you come up with, where you couple processes with one higher recovery rate, one lower recovery rate, you don't actually see this, you don't have this phenomenon where kind of the set of infected particles dominates one and the other, because what happens is when particles recover, the fact they're not becoming susceptible again means that even if you have a slower recovery rate, which means more particles become infected quicker, then it can mean in some sense that more particles die off more quickly. So both of these are actually open. But you can say a few things about this point too, which is trying to essentially establish regimes where the process will die almost surely, or the process will survive with some probability. And actually, just by comparing with the SIS case, it's kind of, once you know this theorem in the SIS case, it's kind of clear that there's going to be a regime where the particles would die out almost surely, because the SIR model is going to be in some sense dominated by the SIS model, because you'll have more susceptible particles around if your particles recover and can become reinfected than if they recover and just are removed from the process. Okay. So maybe, so this is, the more interesting regime is what happens, the more interesting regime to study is the situation where the process survives forever. And this is what I want to talk about. So so what this theorem says is that for all dimensions greater than or equal to 2, there exists some lambda minus greater than 0 such that if lambda is less than lambda minus, then the SIR process survives forever with positive probability. Okay, and so I made this caveat that the dimension is greater than 2. So if, and it's not too difficult to show. It's not trivial, but it's something that can be shown with a little bit less work. So if d equals 1, the process dies out almost surely for all lambda. Okay, so this is what we established, that there is this regime where the process survives forever. But what I think is really interesting about this is, when you're studying this harder model, the SIR model, compared to say the SI model, one thing that you get from studying this harder model is that there's kind of a more interesting phenomenon in this survival phase. So in the way that this survival phase works, you see sorts of kind of lots of cool things happening. So let me give a picture for how the process survives. So we have 3 types of particles, right? We have infected particles, we have susceptible particles, and we have recovered particles. Okay. So the first thing we can establish is that the region with infected particles is growing linearly. So we can't establish a shape theorem, but we can establish that it's growing linearly, upper and lower bounded by some constant. So you see sort of this outer ring, say, of infected particles, and beyond this, you'll see a sea of susceptible particles. Some of these particles turned into a fairly long dashes, but oh well. But what's interesting in the if you're doing this in the SIS case or the SI case, what you'd see inside this ring would be a lot of infected particles. You'd sort of see in the SI case, you're just going to see a whole bunch of infected particles. What you expect to see in the SIS case is kind of some sort of equilibrium between infected particles and susceptible particles, which keep getting reinfected. But what you see in the SIR case is a bit different, right? So what you see in the SIR case is outside of a growing front, you actually have a sea of mostly recovered particles and a few susceptible particles and no infected particles inside this region. So this is a herd immunity region for the infection. And typically what happens is this, and the way we establish it is typically most particles will get infected, but there will be sort of a very low density process of particles that somehow escapes the infection entirely. And so another way you can think about this picture is maybe if you just zoom in on one part of the front here, is it'll look something like this. So you'll see this front. And actually the width of this front is only order 1. So even as you take time off to infinity, the width of this front is really not growing. And on the one side of the front, you see a whole bunch of susceptible particles, and on the other side, you see very few. And on the one side where you have so many susceptible particles that you're propagating the infection. So you're in a supercritical phase here. And on the other side, you have so few susceptible particles remaining that the infection's dying out. So you have a subcritical phase on this side. So I think this is like a really cool feature of this setup is you see a spatial separation, sort of a moving front, where on one side where you sort of have a model with a subcritical and supercritical phase kind of sitting right beside each other, just separated by this infection front, which is kind of forcing all of the particles in the supercritical phase to become infected and then dying, and then you hit into the subcritical phase. Okay, and in the interest of time, I mean, it's a fairly short talk, so I'm not gonna state kind of formal versions of what we have for theorems for how the process survives in the front. But maybe I'll mention at least what we actually can say about the front here. Is we can actually say about the front is if a site is infected at time t, then it will never again be infected. So if a spatial location sees an infected particle at time t, then it will never again be infected after time, say, t plus log t to some small power in t. So I think what we have last I checked was log t. So it's log-ish is what we call this. So the true answer here is t plus log t. Okay, because what's happening is you're sort of taking a union bound over all sites that have gotten infected before time t, and that costs you a log t factor. So we can't quite do that, but we can get log t to some very small power. Okay, so with the remaining time, I'll say something about the proof. I won't be able to get too far, but I wanted to give kind of the main idea for at least getting started for how you say something about a model which is really, it feels very intractable at first. I mean, you're missing such, like I said, you're really missing basic things like monotonicity. So if you try and vary any one of the parameters in this model, you try and vary the intensity of the Poisson process, you can try and vary sort of the speed of the particles. You can try and vary the recovery rate. There's no obvious monotonicity in any of these parameters. So it really is quite intractable. So I'm going to set ft to be the sigma algebra generated by all trajectories, by all infected trajectories, I should say, up to time t. Okay, so you just look at the trajectories of all these infected particles. So you have a picture that's something like this. So you have time going this way, I have space like this. So this is kind of almost a one-dimensional picture. And my infected trajectories look something like this. Maybe they're going to take up roughly a cone shape. And you can ask, okay, what you kind of expect to see this kind of front of infected particles. And you can ask, well, what is sitting right in front of the front, right? What is the process that I see in this set A? Okay. So the nice thing about starting with a Poisson initial condition is that we can say exactly, given the sigma algebra ft, we can say exactly what the process you see is in A. So given ft, the process of susceptible particles in A is still Poisson. Okay, but it's Poisson with now now the density of the Poisson process is going to depend on exactly where you are in the set A, and it's going to depend on the sigma algebra ft. So the intensity here is say at some site X is going to be the probability that a random walk at X avoided the trajectories in ft. So you take a random walk at this site X, run it backwards in time, and you want to make sure that it avoided all of these trajectories in ft. So this teal random walk would not be allowed. Okay, so this is some probability. Okay. And the idea is the following. So we expect our front to be moving linearly, right? If we believe in the shape theorem heuristic here, what you expect is that your front is moving linearly. And if it's moving linearly, then what is this probability? This probability is essentially the probability that a random walk avoids a cone. And because random walks move diffusively, they're not going to have any more trouble avoiding a cone up to time, 2 as opposed to up to time t for say some really large t. Okay, so that's going to mean that this probability is essentially constant, or at least bounded below. And in front of the front, you'll always see, a fresh, independent batch of susceptible particles. So the idea is if the front is moving linearly, then, well, maybe I'll call this px. Then px is, bounded below by some constant for x near the front. And it doesn't decay with t. That's the important part. So you can ask, well, how could we push this heuristic to actually prove something about the model? And the issue is going to be that your front is not moving linearly everywhere. So you can kind of think of this a bit like a first passage percolation process at this point. So you're going to keep running into fresh batches of independent particles, and the front is going to kind of push the infection through these fresh batches. But what's going to happen is sometimes you'll hit a Poisson process in some set A like this, which has, just by some large deviation rule, it's going to have very few particles in it. And that's going to cause the front to all of a sudden move slowly in that region. But then if the front is moving slowly, if you no longer have this linear speed bound on the front, then you're not going to be able to control these px's. And so what's going to happen is, if you no longer have this bound, which gives you a lot of independent susceptible particles sitting in front of the infected process, the whole house of cards is going to start falling down. Okay. So how do you deal with these places which genuinely do happen where the front moves slowly? So how to deal with a slow front? And the idea is you introduce a ghost front, which I'm not going to say in precise terms. So which always moves linearly. So you kind of say, okay, we're going to introduce a ghost front, which is equal to our front, except at places where it's slow. And at places where it's slow, we're just going to let our ghost front kind of propagate at some fixed linear speed, which allows us to ensure that outside of the ghost front, you actually see sort of nicely controlled, reasonably high density Poisson process particles. Okay, so that's the idea. And then you need to show that the parts of the ghost front which weren't equal to your actual front somehow, always get encapsulated by parts that are by parts of your actual front. They sort of, you have these bad slow parts of the ghost front, and then they get kind of closed off by parts of the actual front. And I won't be able to say too much more than that. But this idea leads to maybe I'll say there's like a multi-scale analysis, and then the idea leads to a related kind of deterministic model of competing first passage percolation like processes, which is similar to something analyzed in a recent paper of Sidorvicius and Stauffer. Okay, I'll stop there.
Any questions for Duncan?
So Duncan, if you looked at like a two-dimensional version and you infected half this space, like the left space, and then you kind of looked at the front as it moved to the right, is there any sort of description or sort of effective model for what that growth front looks like?
Yeah, I mean, I think that, I guess you're kind of asking like for sort of a stationary measure for this process, maybe.
Yeah, for instance.
Yeah. I think our techniques aren't refined. I mean, so there should be some sort of, I feel like there should be some sort of stationary measure where you have sort of an order one size front. On one side, you basically have very few particles, and on the other side, you have, you sort of have maybe like essentially say if you're doing this in 2 dimensions, you have sort of a one-dimensional strip, which is your front moving forward. On the one side, you have a sea of susceptible particles, and on the other side, you have basically very few susceptible particles. So you should have a stationary measure like that. But our techniques kind of don't give you that's exactly what's happening. I mean, that's the heuristic that's there. And I'm not sure, like this half space model that you suggested, we could definitely, I'm sure the techniques would be able to say something about it. I'm not exactly sure. I'm not exactly sure what we could say that would be different than in the model that we've studied.
Any other questions? Well, if not, let's thank Duncan again. Yes, Sayan, do you want to share your screen?